Hi everyone. So this is the third lecture on instrumentation amplifiers. We began with the definition of what an instrumentation amplifier is, why is it needed. We said you need to have a very high differential gain and it should be a good voltage amplifier with a very high CMRR. That's the most important characteristic of an instrumentation amplifier. Okay, so we took different realizations, examples of instrumentation amplifiers. So one of you asked, why can't I just build these circuits using breadboards? We argued that matching is very critical to get good CMRR. So usually you would want to put all these op-amp based circuits, op-amps and resistors and everything in a single chip to get good matching. Okay, and we analyzed these 4 different architectures in the last class. Okay, and we saw the problems with each of these approaches. And we said these 2 circuits we said are not good because they don't have differential symmetry. One of them has a problem of poor input impedance as well. And we arrived at this final architecture. We said this guy is great. It has good differential symmetry. It has high input impedance, which is also great. The only problem here was programmability. Okay, I couldn't program the gain without degrading the CMRR. Right? If I just make R2 and R2 external, then I end up risking matching between the 2 resistors it's very difficult to achieve good matching. So external resistors tend to have poorer mismatches compared to the resistors that you can put on a single chip, okay, and fabricate them close together. So that's the main problem. High CMRRs becomes challenging. So now we said this is the architecture we have, which is more or less really a good architecture, but only problem that's missing here is gain programmability. If we can add gain programmability, then yes, maybe I may arrive at the right architecture that I'm looking for. To do that, let's start with a simpler approach. Instead of them being voltage followers, let's add gain in this stage. The second stage, I've just renamed the resistors as R4 and R3, so that I'm just using R1 and R2 and R1 as resistors in the first stage. So in this amplifier, the gain is very simply gain of the first stage, which is a non-inverting amplifier with a gain of 1 plus R2 by R1. That's same for this guy as well. The output voltage is given by this. The second stage is a subtractor with a gain. The gain of the subtractor is R4 by R3. That multiplied by the first stage gain, which is 1 plus R2 by R1. That's your output voltage. It will be V2 minus V1 times this. So this is your differential gain. Now if you guys look at this circuit closely, this circuit is a purely differential circuit, right? It's a differential input, differential output. If it's a purely differential circuit, the ground here, the R1 nodes which I've shown as ground here, I can maybe short the 2 because differentially the circuit is symmetric. I can short the 2 and still expect those 2 nodes to go to ground differentially. Right? They both are the same, they are grounds, but I can short them and still expect that node voltage will go to 0. But I mean, we are just using this simple fact. You have 2 resistors, so I can say something like this. If let's say I have a MOSFET, this is at AC ground, this here is at AC ground, I can argue that I can short these 2 and then apply a differential input here, Vi by 2 and minus Vi by 2 plus Vi by 2 and minus Vi by 2. This node will naturally be at AC ground, differential AC ground. Okay, so I do this and I arrive at an architecture like this. Okay, I've just shorted these 2 resistors and we get I'm replacing with a single resistance of value R, and the feedback resistor, I'm calling it RF in this case. It's just change in notations, that's it guys, so don't be, I'm sorry if there is any confusion there. It's just I've just changed the symbols. So it's RF and R. The second stage, I'm calling it R2 and R1. Now how do we analyze this circuit? So we'll first do a straightforward KCL and KVL based analysis. Then we'll, since it's a differential circuit, we can draw differential and common mode half circuits and arrive at the differential and common mode gains. A very simple straightforward analysis can be easily done. It's a simple circuit. So if this node is at V1, this node will also be at V1. These amplifiers are all in negative feedback. So virtual ground holds. So which means inverting and non-inverting terminals will follow each other. So this is V1. This node will be V2. So the voltage across this resistor will be V1 minus V2. So this is V1 here. This node voltage is V2 here. Okay. So the current flowing through the resistor. So I'll probably exaggerate this part. Hope you guys can see this. Okay, or let me just show this part alone. Okay, so now this node voltage is at V1 and this node voltage here is at V2. So the current flowing through the resistor will be V1 minus V2 by R. And this output node voltage VO1 is simply given by the voltage V1 plus the voltage drop across the resistor, right? Node voltage V1 is simply it's at a higher potential, and the voltage at V1 is simply I times RF plus V1, and VO2, the output node voltage VO2 is simply given by V2 minus the voltage drop. I am assuming the voltage current is flowing in this direction, so there is a voltage drop across RF minus IRF, and I is simply V1 minus V2 by R. So I'll write VO1 is given by V1 plus V1 minus V2 into RF by R, and VO2 is given by V2 plus V1 minus V2 into RF by R. Sorry, this is minus here. This is now fed to a subtractor. A subtractor's output, the output of the subtractor, will simply be R2 by R1. The resistors are R2 and R1 for the subtractor, times V2 minus V1. So that V2 here is VO2. VO2 minus VO1. That's what we are feeding to the subtractor. So now you guys can substitute this VO1 and VO2 in these expressions, and you can easily show that the output voltage is simply given by 1 plus 2 RF by R, so into R2 by R1 times V2 minus V1. Okay, it's just subtract these two. Subtract this from this, you get this expression. This here happens to be your differential gain. Okay, this happens to be the gain of the circuit. So if V2 and V1 are the same, that's output will be 0. So that's the common mode gain is 0 for the circuit. Okay, so it's a very interesting circuit. We started from here and arrived at this. I've just done a brute force analysis and showed you guys what the output will look like. The output has two expressions to tweak. I mean, the gain of the circuit is given by 1 plus 2 RF by R times R2 by R1. Okay, so now if you see, right, the gain, I have two degrees of freedom to tweak to achieve variable gain. We will see a little bit later. So now we have introduced the circuit. It looks like a great option, great differential symmetry, input impedance is infinity. The only thing missing here is programmability in the gain. Okay, I should introduce programmability in the gain without having an impact on the CMRR. That's the only thing missing in the circuit. So first let's analyze CMRR. What does it depend upon in the circuit? So to do that, I'll start with a standard common mode analysis. So I'll assume both the inputs are at common mode. If both the inputs are at common mode, the voltage drop across this resistor at the center will be 0, right? This node will be at VCM. This node will also be at VCM. Both these nodes will be at VCM. If both these nodes are at VCM, there is no current flowing through the resistor. If there is no current flowing through the resistor, the voltage drop is 0. The voltage drop across RF is also 0. So VO1 will be equal to VCM. VO2 will also be equal to VCM. The output voltage will be exactly equal to 0. A very interesting thing happens in this circuit. That is, what if these two resistors RFs are not equal? Remember, the current in this circuit is determined only by the resistor at the center. That's the only guy which determines the resistor, determines the current in the circuit. Even if R2's RFs are different, let's assume this is RF plus delta RF, the voltage drop across RF will still be 0 because these two nodes will still be at VCM. So the voltage across the resistor at the center is 0. So even if these two resistors RFs are not matched in the first stage, it doesn't really matter. The common mode gain, if the second stage is ideal, let's assume the R3 and R4s are perfectly matched. If they are perfectly matched, your CMRR, theoretical CMRR is infinity, which means your ACM is still equal to 0. That's a great idea, right? The first stage is so good, it's fully differential that it's rejecting the common mode completely. Okay, it's even if the resistors are mismatched, I'm getting the same common mode voltage at the subtractor's input. So that's one big benefit of this circuit. The first stage doesn't have to worry, you don't have to worry about matching in the first stage. The second thing is differential gain. We have already derived the expression for differential gain, but since we know how to analyze a differential amplifier using half circuits, what I can do is I can just take this part of the circuit and draw a half circuit and derive its gain. So how do you do that? The resistor R at the center can be split up as two resistors R by 2, R by 2, because these two nodes are differential. This is a differential and this is also, these two nodes are differential. I can split it up as a resistor R by 2 and R by 2. At the center of this resistor will go to 0. So that's what I've shown here. So differentially I can represent this as R by 2 and R by 2. And the gain of the first stage will be now 1 plus RF by R by 2, that will be 2 RF by R. So if you are wondering where did that factor 2 come from, it comes from this. Okay, you can just quickly see it as a differential half mode circuit and you'll immediately see where this factor 2, when we were deriving the gain expression, right, we were getting this factor 2. So I'm just showing you guys, you can directly arrive at this gain expression without even writing all these KCLs and KVLs by directly using this half circuit concept. So the first stage gain is 1 plus 2 RF by R because it's a fully differential circuit. The second stage is a differential to single-ended converter, or you can, it's a subtractor, it's a differential to single-ended converter with a gain of R2 by R1. So that's the differential mode analysis of the circuit. Now finally, the only thing remaining is programmability. If I want to achieve programmability in the gain, so I said when we began the lecture series on instrumentation amplifier, in the second lecture we said the subtractor, the resistors has to be really well matched. So in this circuit, if you looked at this amplifier, instrumentation amplifier circuit, the first stage doesn't add much to common mode, right? We just saw the RFs can be mismatched. Even then I can achieve very good common mode rejection ratio. Okay, it's the common mode rejection ratio for this circuit will be mainly from due to the second circuit, the second subtractor amplifier. So therefore I cannot do any programmability in the second stage. I don't want to add any programmability in the second stage. I would preferably manufacture all the resistors on the single chip. Okay. Now therefore I'm going, all I'm trying to say is, since you cannot do programmability in the second stage, you're left with only adding programmability in the first stage. We saw that the gain depends upon 1 plus 2 RF by R, right? I can either vary RF again I have to take two resistors. I don't want to do that. I can just vary this resistor R alone. Okay, that's the advantage of this architecture. I can just vary one resistor and not worry about CMRR at all. Okay, so I can keep this resistor R alone external and all the other resistors in a single chip. Okay, so that's what I've shown here. The chip, this entire thing, these 3 amplifiers, and what, 1 2 3 4 6, totally these 2 resistors RF, these resistors, and the remaining 6 resistors, and these 3 op amps inside this chip is what we call as an instrumentation amplifier. And the inverting nodes of these op amps, or the resistor is now, we can just, these 2 pins are normally available. If you purchase any instrumentation amplifier chip, you will have these 2 pins accessible to the designer, where you can connect this resistor, programmable resistor, to achieve any desired gain you would want. So now, what are the things that I've checked? High input impedance, check, because you're looking at the non-inverting terminals input of the op amp, high input impedance. That can be in the order of gigaohms, sometimes even much higher, okay, for MOS amplifiers, MOS amplifier based op amps. High CMRR, because the second stage resistors are all inside the chip, so I can control their matching very well. And the first stage resistors, I don't have to worry about its matching because they don't impact the CMRR much. So I can get very good CMRR because the programmability is done using a different resistor. Okay, I've used the terminology RG for this resistor. That's the terminology used in literature. So we program that resistor alone. Okay, great programmability. I could achieve programmability in gain without impacting the common mode rejection ratio. That's the big advantage of the circuit. And there is also good differential symmetry. The first stage is a fully differential structure, so I get very good differential symmetry. So that's why this is the most popularly used instrumentation amplifier architecture. Okay, it gives you benefits over all the other architectures that we discussed so far, and it's the most canonical structure, right? It's very as minimum number of amplifiers and resistors possible. Okay, so you can always claim I can take these old architectures and add some op amps after them and vary its gain. I can introduce programmability that way, but I'm saying that this is the most canonical structure in its simplest possible, very high gain differential amplifier with a great CMRR. Okay, that's why this is one of the most popular amplifiers, instrumentation amplifier architectures that has been in use for a very long time. The next lecture, we will look at one final topic, which is what happens if the op amp's gain is finite. In that case, what happens to its CMRR?